It's time for hydrostatic pressure part 2, and I begin this video with what was the last slide of part 1. I got you thinking about how the pressure on this side of a tank would vary with depth. The pressure wouldn't be the same everywhere along the side of the tank, okay? And then I said that because of that, we would need to use calculus. Let's talk about how we use calculus for this sort of situation. Okay, so I have to provide you with some parameters, like conditions that must be met for what I'm about to say to be applicable. Okay, so suppose that we have an object submerged in fluid, and that could be, something that is actually inside of a tank, or it could be the wall of a tank that's enclosing the fluid. Either one of those is experiencing pressure because of the fluid, okay? And our goal will be to calculate the total force on the object as a result of fluid pressure, okay? There will be some assumptions, right? I said that there's some parameters or assumptions that must be true for what I'm about to say to be applicable. So the object must be flat. If it's not flat, our technique becomes a little more complicated, but for now, let's say that it's flat and that it's within the fluid and it's vertical. So we have a flat vertical surface within or in contact with a fluid, all right? So here's the setup. Here's how it goes. First you have to be aware of is where's the fluid level, like the very top of it, with respect to the object, okay? All right. And say that you're aware of like whatever shape the object has. Again, whether that's a fluid with something submerged in it, or this is part of the tank that's enclosing it, whatever, okay? We've got to figure out where the fluid level is with respect to the object. Now, imagine that you impose the y-axis somehow on that. It doesn't really matter like where or how you put this on there, okay? You can probably set it up either way. Here's all that you really have to worry about. Your surface will span the y-axis from point A to point B, from top to bottom, okay? And we need these functions, these formulas, these equations that do this. If I was to give you an arbitrary spot on the y-axis, I need formulas that give you the width at that spot. Okay, so say I say this spot right here. Tell me how wide it is. Give me a formula that calculates the width. And then give me another formula that calculates the depth. Okay? Where width and depth are as you see them on my picture. Now, if you can do all that, then here's the total force as a result of fluid pressure. It's the definite integral from A to B. We'll need to have the weight density of the fluid. Okay, so that's like force over volume or weight over volume, okay? Water is 62.4 pounds per cubic foot, for example. Then times this width function, and then times the depth function, and then dy, okay? Now, in this video, I'm not going to explain why the integral is set up that way, okay? It has to do with Riemann sums and dividing the surface up into little bitty parts, okay? For this particular video in our lesson at hand, I just would like to tell you that this is how you conceive of the setup. And once you get all that information, this is how it goes in the integral. And then you solve the integral, okay? All right, so let's go on to a problem, all right? I guess what I want to do first is make sure that you can understand what I mean by if y is given, if some point on the y-axis is given. What do I mean by formulas that calculate the width and the depth? I mean, here you can see on the picture what I mean by width and depth, but formulas, like what would that look like and how do they work, okay? So let's say that we have this tank right here. It's sort of triangular shaped like that. It's 5 feet that way, like into the page. Its width across the top is 4 feet and its height is 3 feet, okay? So can you do what I was just saying? Can you give me the depth as a function of y? Can you give me a formula where if I plug in some spot on the y-axis, you get the depth or the width at that spot and the depth? Okay, that's what I mean by depth and width as functions of y. All right, so here's what we do. Let's take our picture, and I've already imposed the x and y plane on it, but let's take like just the front face of the tank, which is a triangle, and put that, and we can ignore the rest of the tank. Okay, because the width right here, if you went that way a few feet, it wouldn't get any wider. Okay, as I've drawn it, it's not getting wider as you go back or something like that. It's uniform all the way through. Okay, so here's how we do it. If I was to take just this triangle and try to put that on the xy plane, let's see, it's 4 feet across on the top and it's 3 feet wide. Could I take that triangle and put it like this? Put it like where this corner is like right at the origin. Okay, and it goes right through the middle of the front of the face of this tank. Okay, so if I did that, then this would be the origin. This would be 0 and 0. But what would this point be? Well, how did you measure that point with respect to the origin? You go up 3, and I guess if it's 4 feet across and the y-axis is right in the middle, then you go right 2. So notice how I labeled that point 2 for x, 3 for y. Okay? Now, in order for me to get you a formula that calculates the width, okay, which is like this distance right here, I need the equation of this line. So here's what we want. What is the equation of the line that goes through the point 0, 0 and the point 2 for x, 3 for y? Okay? Now that's an exercise everybody learns in algebra class. You find the slope of the line and then you solve for the y-intercept. And I wasn't going to go into that in our video here for Calculus 2. I can make a separate video on that. But the line that goes through 0, 0 and 2, 3 is y is 3 over 2x. Okay? Now, if I want to find the width, then which part of the coordinate measures the width? Okay? So like if the point has an x coordinate and a y coordinate, wouldn't it be true that if I doubled the x coordinate, then that would give me the width? That's true. So I take my equation for the line. The equation for this line is y is 3 over 2x. That's valid. It will capture all points on this line, but I solve it for the x coordinate. Okay? And then if I double that, I get the width. So see how I gave the width as 2 times 2/3 y? There's the equation of this line, solve for the x coordinate. 2 times 2/3 y, that's 4/3 y. There's a formula that will calculate the width of the tank if you tell me where you are on the y-axis. Doesn't the width vary along the y-axis? Sure, it gets wider at the top and narrow at the bottom. So you tell me where you are on the y-axis, this will measure the width. What about the depth? Well, so if, say I'm here and I want to tell you, well, how deep is it? Like say, I'm at point 2 on the y-axis. Well, you're 1 foot below the water level, all right? So if you just took 3 minus y, that would be the depth. Like, say this point right here, 0 for x, 2 for y. Okay, the y coordinate's 2. Then 3 minus y will tell you the depth there. 3 minus 2 tells you the depth is 1. And in fact, if the y coordinate's 2, the depth is 1. So 3 minus y for that. Okay, so that's how we can go about getting formulas for the depth and the width that depend on y. They'll need to be functions of y. All right? Okay. What's the reason? Well, because the depth and the width vary along the y-axis. That's why these are functions of y. That's why these formulas insist that we tell what y is. Okay? All right. So let's try this out. Like, suppose I actually did give you that point. Okay? So let's take this same shape that we were talking about, and I say, what are the depth and width of the tank at the spot where y is 2. So if you're right here in that tank, what would the depth and the width be? Well, I had those formulas, right? That's what they were for. The depth was 3 minus y, and the width was 4/3 times y. So at y equals 2, 3 minus y is 1, and we agreed that, yeah, if you're right here, you're 1 foot deep in that tank, okay? You know, no matter where you are, if your y coordinate's 2, you're 1 foot deep. And the width, well, that'd be 4/3 times 2. That's 8/3 feet. Okay, so the width all the way across is going to be 8/3 feet. Okay, remember when I gave you the formula for the width, I found the equation for the line. I solved it for x because it's doubling the x coordinate of any given point that really allows you to find the width. And I doubled it, right? So that's what this does. It's 8/3 feet all the way across right there. No matter where you are in the tank, if you're at coordinate 2 for y, it's 8/3 feet across. Okay? All right, now let's do an example that involves setting up an integral. Okay? Because remember, here's my procedure. You take the surface that the pressure's applied to. You find out how to express the width and the depth as functions of y. And then your integral is made up like so. Weight density of the fluid that's involved times the width and depth as conceived up there. Okay? Bounds of the integral are a to b. That's the bottom to the top of the surface that's in contact with the fluid. All right. So let's see if we can do that now with an example. Let's take the same tank we were just talking about. Why not? We've been talking about that one, so it's on your mind, and we've already done some of the math that we need for it. Suppose I've got this tank, it's full of water. Water happens to have a weight density of 62.4 pounds per cubic foot. Can you calculate the fluid force on the front of the tank? So yeah, sure, the fluid in here is like pushing on all sides of the tank, but we're just going to talk about the front of the tank for now. Okay? What is the force that the front of the tank feels from the fluid that's on the inside of it? Now, let's make sure. Remember, I said that in order for this math to apply, there had to be these two conditions. The object is flat and the object is vertical. Well, this side of the tank is both flat and vertical. That side over here is not. It's not vertical as it's in contact with the fluid. So to calculate the force on this side of the tank, the method would be a little bit different. But with what we've learned, we can calculate the force on the front, the total force as resulting from the fluid on the front of the tank. So let's see. So with this tank, all right, it looks sort of like the last one, okay? It's trapezoidal and not triangular, but we can think of it the same way, where if, say, I'm wanting to know, well, just the front of the tank, can I calculate the width and the depth for that? All right, so here's just the front of the tank. It's trapezoidal, okay? And let's see, I'm gonna need some points. How did I get the points? Well, so look, I put the y-axis so it goes right through the middle of the front face of this tank, see? So if the top of the tank was 4 feet wide, but the tank itself was 3 feet tall, that would be a y-coordinate of 3 and x-coordinates of 2 and -2. That would give you a width of 4 feet right there, okay? And if the bottom of the tank was 2 feet wide, and again, if I'm putting the y-axis right down the middle, then that would make this point at 1 and this point at -1 for x. That would give me a width of 2 feet. So if with just the front of this, or our math is focused on just the front, imposed on the xy coordinate system, those are the lines and points that I see that would make it up. Okay? Now, what is the width and the depth here? You know, there's the width, there's the depth, right? Is there some way you could tell me that? Well, the depth is going to be 3 minus y. The depth right here is 3, which is where the top is, minus whatever the y-coordinate is. And the width, well, I need the equation of this line. So what I would have to do is find the equation of the line that goes through the point 1 and 0 and also the point 2 and 3. Okay? So that's a technique that we learned in algebra class. I told you I wasn't including that in the video, but y is 3x minus 3 is the equation of that line. Okay? Now, that won't calculate the width. You know, this right here, that might be the equation of this line, but that won't calculate the width for me, you know, all the way across right here, because the width right here would be double whatever the x-coordinate of that point is right there. So I'd have to take the line, solve it for x, because it's the x-coordinate that the width is based on. So solve it for x, and then double it, right? There's your width as a function of y. You can go up and down the y-axis, and this formula right here will tell you the width anywhere, okay? All right, so I've got it. Now, what was the integral? It's the weight density times the depth times the width. There's the weight density, there's the depth, there's the width, dy. As I impose the front of this tank on my y-axis, it spans the y-axis from y equals 0 up to y equals 3. So those are the bounds on my integral. So there we go, like that. And factor out some constants, leave the variables inside, and I'll get about 748.8 pounds of force, okay? All right, so that's at least the resulting total force on the front of the tank. Now remember, the sides, that would be different. The sides are not vertical with respect to the fluid, so this technique doesn't apply to them. But you know, the back, that's just like the front. It's symmetric as far as that goes. You could use the same method for the back. You get the same answer. Okay, but for the front, that's what it is. Okay, so now, start to finish, hopefully you saw this. All right, take your shape in contact with the fluid, impose it on the y-axis. It really doesn't matter how you impose it, whether you put it up here or down, you know, it's just got to be correctly with respect to the fluid level and so on. But, you know, once you get it wherever you're going to put it, this depth and width and bounds need to be accurate, okay? All right. In another video, I'll show you how we can take one problem and set it up different ways and get the same answer if that matters to you. If you're worried about how you set it up, it'll allow you to see a little bit of variety. But for now, I'll probably stick with just putting everything, you know, right smack in the middle like that. Okay, let's do another problem. This is one that I started thinking about when I was making the lesson. I imagine if you looked in books and so on, you could find a problem like this. It seems so obvious to me to include this problem, but who knows, maybe as I include this, this will be totally unique. So, consider the terrifying situation of a car driving into a lake, okay, which has happened before, unfortunately. The car becomes submerged to the top of the door, let's say. Maybe it would go deeper, but for our problem, let's assume it's submerged right up to the top and no higher, okay? Calculate the fluid force on the door. Oh, so like if that happened, the fluid in the lake would be exerting a force on the door trying to keep it closed, right? Assuming that the inside of the car is dry. There's no fluid inside the car pushing out on the door. There's just air. And then the lake is pushing, keeping the door closed. So how strong is that? Maybe you've heard that it's really hard impossible maybe, to open a car door if it was submerged in a body of water like that. And I even have this thing in one of my cars, which is designed to be able to break the glass on the window if that should ever happen, okay? So sure, I mean, I guess it's a situation that some people worry about and it could happen. But how strong is that? I mean, how hard is it to open a door if a car was in a body of water like that? Okay, now we'll have to make some assumptions that might not be totally accurate if this were to actually happen. And one, that the door is rectangular. You know, that not true. Sure, it's not true, but it's close enough for what I want to do in this problem to assume it's rectangular. And we'll assume that it's flat and vertical, because those were the assumptions that I said that we needed at this point. If it's not flat and vertical inside the body of water, then the method does become a little more complicated and different than what I'm showing you in this video. Okay, so the door is rectangular, flat and vertical. Dimensions are 3.4 feet wide and 2.4 feet tall. So what's the total fluid force on that door? Well, so I just put the door like this. So our assumption is it's rectangular, okay. The water goes up to here, all right. So like this point right there, that would be 0 for X and 2.4 for Y. And then the water is kind of like this. So 2.4 feet this way, and then I put the door like that to where the other edge of it is out here, 3.4 feet. So like this point would be 3.4 for X and 0 for Y. Okay. So I think with this one, it's probably not hard to give the width and the depth as functions of Y. Okay. Because the width is uniform. This time, unlike this tank right here, how wide the tank is completely depends on the up and down position. It's wider at the top, narrower at the bottom, so sure. But here, the width is the same everywhere. So the width is just going to be 3.4. It doesn't actually depend on Y. There shouldn't be a Y in that equation because the width has nothing to do with the vertical position. All right. The depth, as you're anywhere along the y-axis, it's just going to be the y-coordinate at the water level, 2.4, minus y, your variable position along the y-axis. So the depth at any point on the y-axis is 2.4 minus y. If you told me y was 1, right there, say y is 1, okay, 2.4 minus 1.4 feet under the water. Okay, that's what that's going to do. So, all right. Total force on the door. Here's our integral. As I position this door, it spans the y-axis from 0 up to 2.4. All right, so those are my bounds. 62.4 pounds per cubic foot. That's the weight density. 3.4 is the width. 2.4 minus y is the depth. dy, that's going to be 611 pounds. Could you push out on a door with a force of 611 pounds? Well, maybe you, I don't know. Who am I to say? Maybe you could. I can't do that. I don't know. Maybe if my life depended on it, I could. Still, probably not. So I guess I do have this thing to save me if that should ever happen because I'm just not that strong. Another thing is that this is the force if the inside of the car is dry, if there's not water in it. What if the car were to fill up with water slowly? Well, then the pressures equalize, okay? Then the whole door's underwater, all right? And you've got the water on the inside is pushing out too. So that would change things obviously. But as it is, with it dry on the inside, the water's pushing in, trying to keep it closed with 611 pounds of force. Suppose the car door is not truly rectangular. Well, if it's about this size, then it's probably very close to whatever the actual measurement would be. Okay, but I wanted to include it as an example in the lesson, so there it is. One thing real quick, I forgot to mention. Let's go back to this one. Somebody could react like this. I should have said this at the time. I just forgot to do it though, so I'll say it now. Notice how I didn't tell you that dimension. Okay? It wasn't even involved in the problem, in fact. So why is that? Well, could this have been 20 feet? What if it was 30 feet? What if that tank was 30 feet that way? Would that change the answer? Would that change the force that the water on the inside is pushing against the front of the tank with? You might say, well, if the bigger that dimension is back here, the more water it's holding. So does that not somehow factor into this? And does that not say that the bigger this is, the more water's in the tank and the greater the force of the water on the front of the tank is? Well, it turns out no. In no way was that dimension of the tank involved in our work. It just doesn't matter. Why is that? Why doesn't it matter? Well, because remember we learned in the first video that the pressure in a fluid just depends on the depth. So, like say the pressure right here just depends on the depth. It doesn't depend on the fluid back there, because that's not what the depth is. The depth is, well, if you're here at that spot on the front of this tank, the depth is how much fluid is above it, not how much fluid is behind it or how much fluid is over in that direction. Okay? So to be consistent with our technique, it doesn't matter what's back there. It just matters what's above. And then the truth is, like, yeah, in an actual tank, our method would apply and it's correct, and it doesn't matter what's over here. All right? With respect to the fluid contacting the surface, it just matters at each point of depth on the surface. Okay? All right. So that's how it works. Let's see. Let's do another example. I need to now that I've introduced the basic idea with how the integrals are done, I need to vary things up a little bit. Okay, I need to show you some examples that are all a little bit different from the ones that we've already talked about. So let's say that some of my measurements are different, okay? And you'll have to excuse the dog. Anyway, let's say some of my measurements are different, and I'm going to measure the weight density in newtons per cubic meter. So that's fine, okay? I can do that. It's weight over volume, all the same. And this time I have a surface that's submerged in the water, okay? So this is not a tank. Let's just say it's a plate. And the plate, the water's pushing against it and so on because it's inside the water, all right? So let's say this. Calculate the fluid on one side of the plate, okay? I know that if it was completely submerged in a fluid, you'd be pushing from either side, but what's just the force on one side, okay? And suppose I have a trapezoidal plate, it's submerged vertically, right? It's totally flat. It has to be flat also, okay? If it weren't flat, then our integral and our setup doesn't apply to it and so on, okay? All right, so I don't know, maybe it'd be worth mentioning some of the fine print. If this is just sitting there, okay, and it's not moving, then the net force on it would be 0. And so that's why I'm just looking for the force on either side. I know that the force of the water on either side is the same. So I just want to set a problem up and calculate what the force is on one side, just to show that we understand how to do that. Okay, now I need to take this and I need to impose the coordinate system, specifically the y-axis on it. So here's how I decided to do it. I have the trapezoid there. I have points on it that are consistent with its dimensions. It was supposedly 7 meters across the bottom. Well, from negative 3.5 to 3.5, that would be 7. And it was 4 meters across the top. Okay, from negative 2 to 2, that's 4. I have the y-axis going right through the middle of it. Okay, and it said it was 1 meter tall. So, okay, then from here to there, that's 1. Okay, the y-coordinate there is 1 and 1. All right, so that's all consistent with those dimensions that were given. It did say that the water was 4 meters above it. So like the top of this thing was at a depth of 4. So what I needed to do, or at least the way I imposed the coordinate system on this, was to put the water at 5. All right, so would that be consistent though? Well, if this is at 5 and that's it, where's this point? 1. Then what's the distance here? Well, that'd be 5 minus, that's 4, right? And so that's consistent with the top of it at a depth of 4 meters, okay? So when we do these, I just need to put everything on here in a way that's consistent with whatever the original dimensions of the situation were given. Okay, now, all right, so I guess we can handle this like the others. I need the equation of this line. What my width is through this thing is based on the equation of that line. So this side of the trapezoid, that's going to be a line that goes through 3.5 and 0 and 2 and 1. Those 2 points. And like I said before, that's a standard technique of algebra to do that. So it turns out this y is negative 2/3 x plus 7/3. But like I've said before with the other problems, the width is based on the x coordinate, right? Okay, like if you were to double the x coordinate at any point, you'd get the width. So I take this line, which is accurate right there. That equation is accurate for this line. I solve it for x. And then I double it, right? And I get 7 minus 3y. So the depth is 5 minus y. The depth at any point on the y-axis is 5 minus the y-coordinate. All right, and then the width is double this 7 minus 3y. So our integral, as I've imposed it, this object spans the y-axis from y is 0 to y is 1. There are the bounds on our integral. The weight density, well, that was given to be 9,800 newtons per cubic meter. All right, 9,800. And what's this? The width, the depth, dy, and if you solve the integral, 245,000 newtons, okay? Remember, a newton is a measurement for a force. It's convertible to pounds if you want to. In my part 1, I gave you the conversion between newtons and pounds, but it's just a measurement of force, okay? So yes, the force on one side of the plate as a result of the water, the pressure within the water, 245,000 newtons. Okay. So, in our next example, here's what I want to work up to. I won't do this example now. I'm going to save it for the next video, but just to tell you where we're headed with this, what if we were dealing with like a circle here, a submarine, and say that there's a porthole in the submarine, and it's circular, and it has a certain radius and so on. Could you find the force that the water is pushing on that? Okay, it's kind of like the car door, but the fact that this is circular does change the setup a little bit. Okay, but we'll do that in the next video, which will be part 3.